Welcome. Welcome to the second half of Lecture 11, scheduled for the end of week 4 in an 8-week summer course. In this part, we focus on greedy algorithms and divide and conquer. These are two techniques, and in some sense, you could say this is where the course on design and algorithm and analysis of algorithms really started. Uh, Greedy algorithms and divide and conquer are two very commonly used techniques to design algorithms. So, in this review, I will give 5 more representative problems. Representative for what is in a course in computer algorithms. It's not exhaustive. I will indicate many more variations that we have covered. If you are in a hurry, then this could be the essence of what we have done in the 4 weeks. So in some sense, this could be a summary. Now I give this presentation with answers. So this is the second set of slides that again, if you are in a hurry, could be most useful. But again, we have spent already 4 weeks thinking, analyzing, designing, computing examples that going through this sequence now of 5 representative problems will most likely help you, but it's certainly not sufficient for a deeper and a good understanding of the algorithms. Okay, with that said, let me indicate the 5 representative problems. So this is problem number 6, as we will go to problem 6 to 10. So we are interested in computing all shortest paths in a graph, in a weighted graph. So you could think of we are headquartered in Chicago, and you could think about what are the shortest distances to all other major cities in the United States. So what we have, so it looks like a very complicated problem, and it's a serious problem. We make a mathematical abstraction of this. We have 6 vertices, and we have a number of edges, so where every edge has a weight. So this could be a distance. So there are 2 bullet points on this question. The first one is to execute the algorithm. That is an important step. So you have to know which algorithm here that we have covered. And you have to correctly apply it. The algorithms that we see in this course are extremely efficient, so and our examples are extremely little, so it's all over very quickly. But as you run these algorithms, think about what you're really doing. Tell yourself, I'm doing this because. So and use your, so you can, if you like, already look at the second question, second part when you do the first part. So that's, so second part is usually requiring more reflection. So we want to know what is actually the argument for why the greedy algorithm works. And think about, so when you are at 3 vertices, what happens when you select the next vertex, and why is your selection the optimal selection? Okay, so the algorithm that we are running is Dijkstra's algorithm. So here again, for the sake of presentation, I'm drawing a very nice graph, and in the sequence of slides that follow, I copy that graph all over again. Now, what you actually are computing is one array of distances. It is initialized d of 0 equals 0. So this is step 0. So in essence, you can solve this question without making a drawing. So my slides are intended for a self-contained representation. If you are studying this course, you could start with a review and then go through the steps. So we select now the first vertex because it is of all the vertices that are connected to our start vertex, it is the closest one. And I now see that I've made a mistake in the answer, so the distance is not 0, but it is, of course, 7. I may have confused something here. We are also computing the predecessors. So this would be the distance, and what you can also, the distance from 0 to 1, you could actually also say that this is the predecessor. On the shortest path from 0 to 1, the predecessor from 1 is 0. And indeed, this is the case for the second problem as well. So in some sense, in delivering this lecture, I can make it a little bit more attractive. So we have that the distance is 9 and the predecessor is also 0. So notice that here in this second step, we had to consider all the vertices 0 and 1, and looked at the next vertex we could connect with the shortest path. So 3 could have been considered, but there is distance 15. And 15 is larger than 9, so 3 is not optimal. 4 is not at all connected to 0 and 1, so is not considered. 5 could have been an alternative as well, but you see that 5 is at distance 14. Okay, let's continue. So I'm indeed computing all the predecessors here and not the distance. So the distance from 2 to 5 is actually 11. So that's the distance. And why again? So, and here is, this is important because this is step 3 in the algorithm, where we started with the set of vertices that was selected, 0, 1, and 2, and we had to decide which vertex to add. On the picture, 2 is the obvious choice. So you can't really say it's the choice because it's obvious. You can't also say I'm running Dijkstra's algorithm and it's in my head. No, you have to be capable to justifying why 5 is the next selection. All right, then it is 3. Why again? So I'm going to answer yet. And here again, you see that 3 is connected to 2 and 2 is connected to 0. So this is this path, the shortest path, that is represented by one single array, which I'm here now mislabeled by D. Okay, so then the last step. And why also are there 5 steps? That could be a follow-up question, because what you are actually computing is a tree. And each time we are adding one more edge to a tree. We have shown, because it's such an important property, that every tree on n vertices has exactly n minus 1 edges. So if you are running on 6 vertices, if you're running 10 steps with Dijkstra's algorithm, something awfully has gone wrong. That's another way why it is important to understand the properties. Okay, let's go to the follow-up question. Another follow-up question would be to compute now to list all the paths from this output. So that was in one of the homework exercises, which I hope you were able to solve well. Okay, so let's go to the follow-up. Why is it correct? So, and I'm giving a snapshot of the answer. So in some sense, in my slides, it's one sentence, and that's very minimalistic. I should say that I'm kind of restricted by the medium of the slides. So I try to be on the sentence as complete as I could be. So in step 3, we have already selected vertices 0 and 2. Why is the next vertex 5? Because it is the shortest length, and that is 11. So 11 should have been the value that is added in that vector of distances. It's the of all the vertices that we could consider, and here I'm actually explicitly saying what should have been added to the slide. So we could have considered also 3 and 5. We could have considered also 3. That would have been the other choice after selecting 1 and 2. But you can see that the distance, so I'm saying it's the shortest length is 11. But if you would have picked 3, then 3 is connected with distance 11 and 15. And that is connected to 1 and 2, and we are interested in the shortest path to 0. So the path that would have led to from 3 to 0 would have been at least 20. So this is what is still lacking on the written portion in this answer. So I'm saying here now that you should have said it's the shortest one because 11 is less than 20. And we would have had 20 if we selected 3. That's the alternative vertex. Okay, that's one problem solved in 10 minutes, and I have, well, less than 50 minutes. If you solve this question, take at least 10 minutes and take time to understand the question. For the minimum spanning trees, we have seen 3 algorithms. Here I'm running only through one of these algorithms, the algorithm of Kruskal. And I'm actually giving the same weighted graph as the one on Dijkstra's example. Note that we also spent ample time on justifying why Dijkstra's algorithm could not be applied. So what is a minimum spanning tree? It's a selection of those edges so that the sum of the weights of all the edges that you selected is minimum. It's also obvious that you need to, so you are starting with a connected graph. That was implicit in Dijkstra's algorithm here. So we want a subgraph of a connected graph that is minimum. And again, it has to be a tree because everything has to be connected. And the characterizing property of a tree is that it is the connected graph with n-1 edges. So if you have a connected graph with n-1 edges, then it has to be a tree, no matter how you draw it. Okay, we will run the algorithm of Kruskal, and in some sense that's a start. It also makes the lecture self-contained. So if you are not at all knowing what is Kruskal, you should look to the lectures. Here we are presenting a very short introduction by example. When we studied the design and analysis of algorithms, we were always very clear to spend time on the problem statement, We gave examples of inputs. Here we only see one example, which is in a way representative, but not not at all. What is the essence? Because it's an efficient algorithm of Kruskal. It runs in time m log n. So the m is the number of edges, which can be quadratic. So it could still be a sub-cubic running time in the number of vertices. But with the union find data structure, we have shown that we have an m log n bound. So what the second part of this question asks for is the main argument. Main argument here is important. You will not get much credit if you dump all the slides or copy and paste what is in the textbook. So that's just not listing the main arguments. I should um, emphasize that again. Okay, so how does Kruskal work? Well, we are it's an edge-oriented algorithm. We are starting from a graph where we have sorted the edges. So in some sense, I draw the graph again, but for running the algorithm, it's sufficient that you see the sorted edge collection. So you have to sort a very small set of numbers. And it's good to have some visual representation of the algorithm, although again, it's not a necessity. It's to make the presentation more attractive and self-contained. So we are going to start by selecting the edge that has the smallest weight. If you're traveling, you want to reach, you have to travel, you go to the first city that is closest by. Okay, here it is then. So we select now edge 2, and that leads to the inclusion of 2 and 5. So I'm making a drawing, but you could essentially also just indicate, hey, this is what I'm selecting. The next selection is also obvious because I'm not having a tree, so I can add the vertices 3 and 4. I'm actually now having a disconnected graph. Then the next step gives me 2 more vertices, but 3 components now. Obviously, the sum will be minimum of all the weights because I have selected the minimum edges. Okay, then I'm starting to connect. Note that the algorithm of Kruskal continues till you have connected all the vertices without introducing cycles. So a tree has so few vertices, so few edges that there can't be any cycles. There's no room. So here you have to be careful when you add, and here is now my next, well, there's actually not that much choice here, isn't there? But it could have happened, and perhaps this is not an interesting example here, if the distance between 1 and 2 was 5, or was actually, if this was swapped, so to make this more interesting, then 1 and 2 would have been a better choice as far as the minimal edges goes, but 1 and 2 would have introduced a cycle. So you must not add cycles. That's what you have to be mindful of. You construct a tree on 6 vertices, you have 5 steps. That's another important property to remember. So the graph at the right is a tree. It might not be obvious. If you tilt your head a little bit, it is. So here is actually the minimum spanning tree. Okay, is this now an efficient algorithm? in one sense, you could say, well, we only have n minus 1 steps, so it's a linear time algorithm, linear in the number of vertices, but that essentially disregards the data structures that you should be using when you're implementing an algorithm. So, I'm a practical computer scientist. I develop software. An algorithm on paper is not at all equivalent to a computer program. You can only get to a computer program when you have selected data structures as well. And for this course, when we analyze whether an algorithm is efficient or not, we must declare and define and specify which data structure that we will be using. We will be introducing the union find data structure. So that is the second part of the question. So I should have flashed it up again to remind you of what the question is. And here you see the running of the algorithm again. We actually start with a set of vertices, no edges at all. And that is represented by this union find data structure, is that we have 6 different components. Every component corresponds to one of the vertices. So now we're going to run the algorithm again, but pay careful attention to how this union find data structure changes. So we are adding edge to 5, and 5 and 2 were in separate components. 2 was in component 3. So we start labeling our components by 1. It's okay to count from 0 as well. But you see component 3 contained 2. And now component 3 will also contain 5. So in this way, we indicate the connectivity data structure. Then we add 3 and 6. So the components that contained 3 and 4, I'm sorry, we adding 6 as the weight. 6 is the weight of the vertex, weight of the edge connecting 3 and 4. So 3 was in component 4, 4 was in component 5, but after this addition we have 4 as the component indicated in this union find data structure, which is, as I forgot to mention, is represented by a one-dimensional array. So we have a one-dimensional array, a very efficient data structure. That's already very good. So why do we still have not a linear complexity? Well, let's wait for that. So we add then the nodes 0 and 1. So we merge vertex 1 to vertex 0, the same component. And then we are merging 2 components, two-dimensional components, changing the labels of the vertices 2 and 5. So now they are both in the same component number 1. And finally, in the step 5, we have only one component left where everything is connected. Again, if you run this on the example, it seems very straightforward, but know what is actually happening and how things are happening. And why? Why is this now an m log n algorithm? Why do we have m again? Well, here is the summary of the arguments. So we have to be very careful on how we work on that array. Also, the example was probably too small, and we never added one very small component to a very large one. So they were always balanced. But when taking the union of two disconnected components, you adjust the labels only of the smaller set. As a consequence of that, when we take K union operations, we have that the set can be at most double of the union. Or likewise, we can change only at most half of the elements in a set. So that was an important lemma, or an important stated as a theorem here. You should not recapture this entire argument, but be able to summarize. That's in the main point. So we have this n log n, and so okay, we thought it was linear because we had n minus 1 steps, but we have the cost of working with this union find data structure, which is an array. So and we have to be careful, because actually working with an array, if you have to modify all the elements, and we've actually seen in the lecture how it can go wrong if you are adding to a small component a large component, and you always relabel the large component, then you do have n steps for this union find. But here it's at most a logarithmic cost. Okay, where does the m come in? Well, even though we do only n minus 1 steps, we have to consider actually all our edges. So it's an ordered step. We may have to find the edges. So in that union data structure, we have the constant of the order m. So that's why we can change the n log n into an m log n, which is a bit neater because we're going to add that order of m there. Okay, so this went rather fast. So this is summarizing an entire lecture. So again, if you have skipped the lecture, or if it's too long ago that you have seen it, then this might be very short, too short. Okay, so one spanning tree algorithm covered. We have seen Prim's algorithm, which is a vertex-oriented algorithm, and for which the priority queue was the data structure. We have covered the reverse delete algorithm, which is an alternative edge-oriented algorithm, which starts by deleting edges rather than adding to them. And for that, actually, I suggested the breadth first search tree as the data structure needed to implement this algorithm. So these are two alternative algorithms that I expect you know, and you know how to analyze. Again, the answer, and that's what I have to emphasize again, this is a very complicated argument, but I was only asking for a couple of sentences in the argument, not the entire reasoning. Okay, three more problems to go. Problem 8. So this is another greedy algorithm. So we will see three greedy algorithms and two divide and conquer ones. Scheduling. Programming in the older sense was often synonymous with scheduling, not so much coding as the more narrow point is. Okay, we have one resource here, and we have a number of requests, and for each request we have the start and finish time. This is a discrete course, discrete problems, discrete algorithms, so the times are very nice integer numbers. We want to schedule those requests on our resource and to minimize the maximum lateness. for the review, this is kind of a good problem to kind of show the flexibility. When we were thinking about minimize maximum lateness, oh, okay, so I should first say that what means scheduling. We have only one resource. You can see that the last two requests overlap. So if you want that everything finishes between the start and finish, then it's obvious that you can't schedule all 6 of them. But note that the question asks for the maximum lateness. So the last job needs to be finished at time step 21, but you can't do it because of the overlap. Now, you can still do the requests, but it will be past the finish time. The finish time is here now interpreted as the deadline. So it is the keyword minimize maximum lateness that is actually the key to deciding which scheduling algorithm that you should run here. The follow-up question actually also gives it away. It's a greedy algorithm. How do we justify that the local choices that we made give us a global optimum solution? And for that, you have to show how to apply an exchange argument. Good. So this is the second set of slides. In a more extensive preparation for the midterm exam, you have now looked at the relevant lecture materials and the relevant sections in the textbook. Let's do this. Again, the earliest deadline first algorithm is a very simple algorithm, and you won't have that much credit for actually running it. Every finish time is now interpreted as a deadline. And when we covered the earliest deadline algorithm, earliest deadline first, we were giving the input as a list of tuples, a sequence of tuples, ordered on the second element in that tuple that contained the deadlines. Now you could interpret this as that these finish times are kind of the desired finish times. Think of a contractor who has to do a job for you. You would really like that it is done before that time, but it should be done anyway. So if it can't be done, then you know what, make it happen. And the imagine that you are a scheduler for a contractor who has outsourced this to you. Even if there are missing of desired finish times, you should be able to argue, look, I could not do any better. So the arguments are again very important. All right, in the earliest deadline first algorithm, the next job starts when the previous job finishes. So you can see that we compute start times, finish times, and they neatly lined up. I have already computed the maximum lateness. So you can see that the maximum lateness is the 6th job. So there is no lateness for the first job, but the maximum lateness is 26. Question: running a very simple algorithm runs in linear time, and we have so much lateness. Couldn't we really not have done any better? Now, all possible orderings is 6 factorial, and even already 6 factorial, you may not want to do this. You may want to reason on this. And here is the exchange argument that is used now. Again, I'm immediately showing the solution. And if you know the exchange and argument, you say, of course. So let's look at the last request. So the last request was scheduled last, and it has the most lateness. Well, suppose that you would have scheduled it first or earlier. So that would give an inversion. So we defined an inversion in a schedule as a request that was scheduled before a request with a later deadline. And we have demonstrated that even if you can do this, so the algorithm would never compute this, then you would not increase the lateness. So if you can do this, if there are other optimal schedules that allow you to have inversions, then they will not influence the maximum lateness. And I'll ask you here to repeat this argument by saying, look, if I schedule request 6 before request 5, then indeed, because there were 3 units before, then the lateness drops from 26 to 23. So request 6, customer 6 will be happier, less lateness. But because of the inversion, because customer 5, request 5, was now scheduled 3 units later, the lateness of that customer goes from 24 to 27. And 27 is larger than 26. So, and that's the general property that you have. In the lectures, and again, I invite you to consider these lectures, we were making very nice picture arguments of this. And you can also demonstrate this with a picture showing with the length of the intervals. And this is the key argument to demonstrate the optimality of this greedy algorithm. Okay, 2 problems left, 10 minutes left. Again, this is unrealistic, but I have prepared this very well. I know the material very well. If this is your first time seeing this, it will work, self-contained, but also 5 minutes is actually too little to fully comprehend the solution to these complicated problems. Okay, we are looking at counting inversions. If you have a sequence that is not ordered, so we considered a sequence to be ordered if it is in order of small to large. You might be interested in how much disorder is there, and you can count the number of inversions. We've defined an inversion as one number that is out of place. So 8 is the largest number here. It comes before 5, so it makes one inversion with 5, but since it is the largest number, it makes 7 inversions. So this is a sequence that's quite out of order. Now, the algorithm to count the inversions is a variation of merge sort. And you have to explain why counting the inversions, and if you have to implement your own merge sort, you may just as well return the inversion count, which kind of says how much how much work merge sort really did. You have to indicate again the key argument. Why there is not much work, more work. Why this is still an n-log n algorithm. And illustrate the key argument when you run on the example that you run. Okay, so in some sense this is a review, so we can go fast, but also the purpose of the review is to show how you can actually write very fast solution. In the lectures, we used the geometric arguments by counting the crossings. Again, if you make a very nice drawing, it's welcome, but you have to solve a number of problems within 100 minutes. So this is here a way to help you. How can you solve this fast? Well, merge sort is again a very fast algorithm. On 8 numbers, you have to cut 3 times in half. Each time you solve, you sort the base cases. So you remember the number of swaps you did. So 8, 5, there is a swap. 2, 4, no swap. 1, 6, 6, 1, there was a swap. 3, 7, no swap. So with this bracketing notation, the tuple that is returned, the sort and count returns the sorted sequence, and the first number is actually the number of inversions. If you are a practical person, think about sorting arrays in place. You could have one extra argument up front or at the very end to record the number of inversions. Okay, so then the merge happens. Why is it now very efficient? So if you look at, I will actually use this argument here. So we are merging 5, 8 and 2, 4. 2 is smallest and 2 makes 2 inversions with 5 and 8. 4 is less than 5, it also makes 2 inversions. So that's why we have the 1. The 1 is copied from the 1 swap. Actually, pedantically, I should have written 1 plus 0. But that's actually the 1 plus 0 that is there. So I will add up the sum and write 5 in the next step. So then you can see that at the next merge, every time when the top element of the second sublist that you merge is larger than the first list, you add to your count the number of elements in the first list. So instead of counting the inversion one by one, the natural algorithm to do this would be a quadratic time algorithm, perfectly fine for 8 numbers. But instead of doing 1, 1, 1, 1, 1, you actually follow merge sort, divide and conquer, and you add each time relatively large numbers. So here this sequence had a disorder count of 16. Okay, I essentially already explained how the algorithm worked, also by motivating what I was doing. So if you run an algorithm, talk to yourself and actually explain to yourself what it is actually what you're doing. That also actually helps for you not to make any mistakes. So it also slows you down a little bit. Okay, so here is the key argument of the cost, why this is an n log n. We have only one extra addition that happens, and the depth of the tree is actually logarithmic. When we merge, we have to at most suppose that the top element in the first sequence is larger than all the elements in the second sequence. Then indeed we have to add as many times as the length of the second sequence. So we still have a linear merge cost. But that's also the cost of the merge. So we may need to have a linear number in the size of the problem on the size of the list. Now, you could say you haven't really solved it because you have to illustrate. Well, I illustrated by talking while I was executing. So the answer here is listed in the full abstract language. We're reasoning on n. You could derive it, so you could actually extrapolate your narrative while you were justifying for yourself that the steps that you were doing, they were correct. That is actually the um, correct way of doing it. Similarly, how I solved the first question in the previous pre-recording by deriving. Last question, or actually I was too quick. So here is the illustration. So the illustration, I did it already in words, but here it is now explicitly spelled out. Why you get to the 2 plus 2 and why we actually see that the number of addition is bounded by the number of elements. Okay, now the last question. Divide and conquer. It's an algorithm that you know. If you want to, so we use divide and conquer, and also pointed this out. The straightforward algorithm for the conversions ran in quadratic time, and we reduced it to an n log n, a sub-quadratic time, or as I prefer, a quasi-linear algorithm. Now, if you have a linear time algorithm, you can still reduce it further to a sublinear algorithm. And that is the example or the last question that follows next. If you have to compute x to the power n, then this requires n minus 1 multiplications. You do it straightforward way. But we know the divide and conquer technique. We can actually do a lot better. So think about computing x to the power 4. You compute x to the power 2, and then you multiply x to the power 2 by itself. So you get x to the power 4. So you are getting away with one less multiplication. Doesn't matter much, but think about 8. So you divide and conquer, we can do x to the power 4 with 3 multiplications. And we need one more multiplication for x to the power 8. So that means that instead of 7 multiplications, I got away with 4 multiplications, half of it. Well, that starts to be becoming substantial, but you can do even much better if you think about 16. So the divide and conquer will actually lead you to the logarithm of n. Again, with n equals 8, 7 multiplication straightforward, 4 if you do with 8. So you can already see a little bit picky. So this should have been 1 plus the logarithm of n. So we understand the questions and we are able to correct them. So formulate the algorithm and actually prove that you indeed have a reduction by divide and conquer from linear time to sublinear time. Good. It is good to reduce. I'm sorry now, here I see that I can indeed do it with 3 multiplications, so forget my correction in the previous slide. I was running too fast because here I'm simplifying the problem to values of n that are powers of 2. And then actually it is the repeated squaring method. But since this is a review problem and we want to be a little bit more complete, we are considering any n, and for that n we will consider the binary expansion. So here this is a derivation of the algorithm by example. It's a recursive approach, but again, if you're not careful with the recursion, When you compute, say, x to the power 4, you compute x to the power 2 and 1/2, x to the power 2 and another half. If you did two multiplications, then you won't save anything. So you have to remember this x to the power 2. So that's why the natural, straightforward way of writing things down works well. Here is now the algorithm. So prove the bound on running time. You can reason directly on the iterative version, which for this so the base case, so you assume here that p is at least 1. So the non-negative integer, if p is 1, well, then you don't do anything. The logarithm, the 2 logarithm of 1 is 0. Okay, so we do have actually the upper bound. Okay, I was thinking about any general power when I was explaining the question. And it is a little bit more complicated. What if you don't have a perfect power of 2? Then you can get away with a data structure that is logarithmic in the size of the number. And in some sense, you already have the data structure because internally in a computer, everything is binary. So you have p bits. If again p is the exponent, but in general you will have the 2 log, and you may have to work with the seal. Now I derive the algorithm here by example, showing that if you have working with 7 and not 8, then you also actually need 3 multiplications. So that's why we now have the 2 logarithm of 7 is not an integer number, so I have to take the closest integer number. And I think when I did this, I was a little bit too cautious. I added +1 to it, and that might have been not necessary. Okay, so in the derivation of an algorithm, what you do is you look at the binary expansion and you start multiplying those powers, those perfect powers of 2 whenever you have a non-zero bit. Now be careful here, if you don't do it correctly, it could be that you do still have a number of terms in this product that is logarithmic in the size. And these powers can actually be logarithmic again. So looking at this naively, you may say, look, we don't have logarithmic in n, but we have the square of the logarithm. So that's why this answer is still not complete. I still have one more slide left, even though I'm going over time. So you have to reason that you have no more than a logarithmic +1 multiplication in storage. So this is why I was so careful here with this +1. So when we are computing the repeated squaring, we have actually already computed all the lowest ones. So that means that we have to compute only the highest non-zero bit. We get all the other ones for free by storing them. And this explains the number of storage that you need, no more than the number of bits. And actually, if you have your binary expansion, you already have your bits in there. And that's essentially the argument that closes the justification that you can with divide and conquer. One can reduce the linear, straightforward exponentiation to an algorithm that runs in sublinear time, almost constant. Okay, I hope that these two review sessions were interesting, that it gives you kind of an overview of what has been covered, of what kind of problems that we are currently are able to solve.